DRPI approach to solubility enhancement of a poorly water-soluble anti-gout drug using HME technique. What is HME? HME is a hot melt extrusion process which is used in pharmaceutical industry to create solid dispersion, often to improve solubility and bioavailability of a poorly soluble drug. In this method, the API and polymer are introduced from the hopper, which are then melted and simultaneously mixed to form a homogeneous mixture. This mixture is then extruded through an orifice to form exudates. These exudates are cooled and solidified and then milled to get a solid dispersion. The key aspects are it's a continuous process. It produces amorphous solid dispersion and it is used to improve solubility and bioavailability. Advantages: it's a solvent-free process. It reduces production time. It can help in taste masking and it also used in controlled release formulations. Drug profile: Drug X is an anti-gout drug belonging to category non-purine selective inhibitor of xanthine oxidase enzyme. Oral absorption is 69% of the dose. Log P is 3.8, half-life is 5 to 8 hours, PCS is class 2 drug, and melting point is 328 degrees Celsius. Rationale: Drug X is a BCS class 2 drug having poor solubility in water, which is 0.01 per mg per ml. Solubility of the drug needs to be increased so as to increase efficacy. Next, the drug is a thermostable drug, so it has the ability to withstand high temperatures using HNE method. HME can produce amorphous solid dispersion, which can increase the solubility of the drug. Aims and objectives: to create solid dispersion by using HME, to perform solubility studies and evaluate the in vitro resolution of solid dispersion, to optimize and evaluate the formulation. Methods and result. Key ingredients used in solid dispersion are two excipients, which is Patrick's MXP488, which is used as a polymer, having melting point 40 to 45 degrees Celsius and degradation temperature more than 25 to 50 degrees Celsius. Partex M200, that's a plasticizer, having melting point 166 to 168 degrees Celsius. To know whether the drug can really form a solid dispersion with the polymer, a method called vacuum compression molding was used. In this method, drug and polymer were taken in 1:9 concentration in this machine called melt prep VCM, and they were compressed to a small disk. Due to the immense pressure, the mixture starts to melt and mix together, which in solidifying forms this disk. If the disk is transparent, then the drug is said to be soluble in the polymer, giving a clear appearance. Whereas if the drug contains some particulate matter, as shown in this picture, solid dispersion is said to be formed. Preparation of amorphous solid dispersion using HME. Three formulations, ST1, ST2, and ST3, prepared having variable concentration of drug and polymer, whereas the plasticity concentration was kept constant at 10%. In the development process, the drug and the excipients were uh, introduced in the etching machine to the hopper, which were mixed, melted, and converted into homogeneous mixture. Then it was extruded through a small orifice, leading exudates. These exudates were cooled and milled to form solid dispersion. Evaluation of solid dispersion. First is DAC studies. In studies, drug X shows sharp and intense endothermic peak. Uh, this endothermic peak suggests the presence of a crystalline compound. But in the solid dispersion ST1, ST2, and ST3, there is no such peak seen. Hence, we can say that there is conversion of crystalline to amorphous form. XRD studies, which in this the graph of drug, polymer, and plasticizer shows sharp, intense peak, suggesting that they are crystalline in form, whereas the graph for the exudates does not show sharp peaks. This suggests that there was conversion of crystalline to amorphous form. Evaluation using solubility and dissolution studies. Solubility studies in water suggested that ST1 formulation enhanced solubility of the water greatly as compared to the other two formulations. Uh, in dissolution studies was performed in 900 ml of pH 1.2 buffer. Apparatus used is USB Type 1 basket with speed 800 RPM and temperature 37 plus minus zero point 0.5 degrees Celsius. In this graph, the green colored curve shows the lowest resolution is of the plain drug. From this graph, it is clear that the SD1 formulation enhanced solubility of the drug more efficiently as compared to the other formulations. SD1 is shown in the blue color line. And this formula was selected for further optimization using CCD model. CCD, that is Central Composite Design, was used for optimization in which two independent variables, processing temperature and screw speed, were taken at two different levels. Low level indicated by -1 and high level indicated by +1. And these are the values. Then the effect on solubility and improved resolution was seen in CCD design. The software used was Design Expert 13.0. Number of factors used were 2, number of levels 2, replicate 0, number of center points 5, and the total number of runs were 13. These are 13 runs which was shown in the CCD model. Now, there are the independent variables x1 is processing temperature, x2 is the screw speed, y1 is the active salinity, and y2 is in-video resolution in pH 1.2 buffer. Optimization results. These are the counter plots showing the influence of temperature and screw speed on salinity and resolution at 16 minutes. The first two plots are for salinity and the next two are for resolution. One axis here indicates screw speed, whereas the x-axis indicates the processing temperature. The first plot indicates that salinity increases with the processing temperature, as shown in this region, whereas there is no significant change effect of the screw speed on the salinity. The same is shown in case of 3D surface response curve, where as processing temperature increases, salinity also is shown to be increased. Whereas in case of screw speed, the salinity does not change as much. In case of dissolution, the similar conditions were observed. As the temperature increases, the dissolution also increased, but the screw speed does not have a significant effect on the dissolution. Optimization results. The uh, overlay plot considers all target responses values simultaneously and highlight the area that meets all the criteria. The yellow colored region is known as the design space, in which uh, it's a design space. From the design space, a suitable point is selected from the center part, and it is used for optimizing the formulation. Processing temperature from this we got was to 35 degrees Celsius and flow speed as 25 RPM. The solid dispersion produced using this data were evaluated for the solubility and resolution. Solubility was 0.101 mg per ml and in resolution was 89.48%. SWOT analysis. The strengths are it improves solubility, it's a continuous process, and a solvent-free procedure. Weakness, excipients can degrade at high temperature. Reprocessivity is a problem because the amorphous nature of a drug in the solid dispersion can be unstable, and the drug may be crystallized over time, potentially affecting the drug release and efficacy. Opportunities used to improve viability and also using combination therapy. We can create combination products containing multiple API, potentially leading to the synergistic effect. Threats are the cost. It has high cost of production as well as the equipment cost is high. Regulatory approval landscape for HME process and formulation can be complex and require careful consideration. Conclusion. Amorphous solid dispersion were prepared successfully using HME approach. The optimized amorphous solid dispersion enhanced solubility of the drug by 6.73 times. Dissolution of the drug from solid dispersion was increased by 1.5 times as compared to the plain drug. HME approach can be extrapolated to enhance solubility of other BCS class 2 drugs. These are the references. Thank you.